So far in our discussions of graphing, we've considered data obtained from one variable, either categorical or quantitative, and we've learned how to describe the distribution of that single variable using the appropriate visual displays, as well as numerical measures of center and spread. Next, we're going to be visualizing our association of interest by exploring the relationship between two variables.
Recall that our basic research question is simply whether or not two variables are associated with one another. So is there a relationship between gender and test scores?
Is there a relationship between the type of light a baby sleeps with and whether or not the child develops nearsightedness? Are the smoking habits of a person related to that person's gender? Or how well can we predict a student's freshman year GPA from his or her SAT score? Before we test our own association of interest with inferential statistics, we're going to work on visually describing that relationship. It's important to understand that when studying two variables, each variable has a role to play. That is, a variable may either be a response variable, also known as the dependent variable or outcome variable, or it could be the explanatory variable, also known as the independent variable or predictor variable.
At this point, I'm going to be asking you to impose a causal model on your research question. To do this, you'll need to designate which of your variables is the explanatory variable and which is the response variable. Note that we can only impose a causal model rather than actually test for causation because we're working with what's known as observational data. In other words, the data sets that we're using are based off studies where the sample is simply observed rather than being manipulated or influenced in any way, as it would be in an experiment. Even though we won't be able to be certain that the association we're testing is causal, for the purposes of exploring our question, it remains important to determine the role that each variable will play in our model.
This role type classification can be summarized and easily visualized in this table. This classification system serves as the structure for the rest of this course. You'll find that not only does it help you to construct graphs, but it's also the basis for selecting statistical tools that can be used to explore the relationship of variables that you're interested in. The tools for statistical analysis and for visually representing the relationship between variables is based on the role and type of each variable, whether response or explanatory, and whether categorical or quantitative. To get the hang of this, let's go back to some examples and determine which of the role types represents each research question. If we want to explore whether the outcome of the study, the test score, is affected by the test taker's gender, we would designate gender as the explanatory variable and test score as the response variable. If we want to explore whether the nearsightedness of a person can be explained by the type of light that person slept with as a baby, light type would be the explanatory variable and nearsightedness would be the response variable. If we're examining whether a student's SAT score is a good predictor of their GPA freshman year, the SAT score would be the explanatory variable and the freshman year GPA would be the response variable. If we want to see whether a person's pass-fail outcome on a driving test can be explained by the length of time that they practiced driving prior to the test, time would be the explanatory variable and driving test the response variable. For our sample research question, we've decided that smoking will be the explanatory or independent variable and nicotine dependence the response or dependent variable. More specifically, we're interested in the level of smoking at which nicotine dependence is experienced. How do we examine the association between two variables graphically? When we graph the association between two variables, the independent or explanatory variable is plotted on the x-axis. The dependent or response variable is plotted on the y-axis. This is a most important convention to use when graphing relationships. However, before we actually construct our graph, there are a few questions we need to ask about the types of explanatory and response variables that we'll be working with. The first question is, what type is the response variable? Is it categorical or quantitative? For our sample research question, the response or dependent variable is nicotine dependence, which is categorical. Next, we need to determine how many categories are in this response variable. Since nicotine dependence is coded 1 for yes or present and 0 for no or absent, we have 2 categories in the response variable. The next question to ask is, what type is the explanatory variable? The explanatory or independent variable is number of cigarettes smoked per month. As we saw in the demonstration of histograms, this is a quantitative variable. Since it won't be visually meaningful to examine a bar chart with a quantitative explanatory variable on the x-axis, when our response variable is actually categorical, before we start to graph, it's important to bin our explanatory variable into categories. That is, in order to visualize the relationship that we're interested in, we need to add some data management that will allow us to construct a C2C or categorical to categorical bar chart. To convert a quantitative variable into a categorical variable, we begin by looking at the frequency table for the explanatory variable, number of cigarettes smoked per month. We could use the cumulative percent column to make decisions about grouping individuals into quartiles, roughly 4 equal groups in size, or even quintiles, 5 equal groups in size. However, in this case, it seems a better decision might be to create more meaningful smoking groups based on specific quantities. Cigarette packs contain 20 cigarettes each. We're going to create a new variable that estimates the number of packs that each individual smokes per month rather than the number of cigarettes. This could be a step closer to a categorical variable that's meaningful. Returning to the program, within the data step, where all data management is conducted, we add the following syntax: packs per month equal numsigmo_est divided by 20, semicolon. The new variable is packs per month, and it's set equal to the number of cigarettes smoked per month divided by 20, followed by a semicolon. Then we add this new variable, packs per month, to the table statement so we can view this new frequency distribution. Packs per month is still a quantitative variable, but now we can more easily create groups based on number of packs smoked in a month. After examining the frequency distribution, we decide to create groupings that include those who've smoked 1 through 5 packs per month, 6 through 10 packs per month, 11 through 20, 21 through 30, and then 30 plus packs per month. To do this, we need to add the following syntax to our program. Here we tell SAS if packs per month is less than or equal to 5, then pack category, our new variable, is equal to 3. We chose 3 because it's roughly the quantitative midpoint for this category. Else if packs per month is less than or equal to 10, then pack category equals 7, again, roughly the midpoint. Else if packs per month is less than or equal to 20, then pack category equals 15. Else if packs per month is less than or equal to 30, then pack category equals 25. And finally, else if packs per month is greater than 30, then pack category equals 58. Again, 58, if we examine the frequency distribution, is roughly the quantitative midpoint. Again, and as always, all of these statements are ended with a semicolon. When we add this new variable, pack category, to the table statement, and then run the program, we can examine the frequency distribution for the new variable. With this new categorical variable representing packs of cigarettes smoked per month, we've retained as much of the quantitative features of the original variable we could manage, while also assuring the graph will be interpretable now that the explanatory variable is categorical. back to our graphing decisions flowchart. Now that we've collapsed our explanatory quantitative variable into categories, we're ready to make our C2C or category to category bar chart. When graphing the relationship between a categorical explanatory variable and a categorical response variable, we use the code proc gchart semicolon vbar categorical explanatory variable / discrete type equals mean sum var equals categorical response variable and end it with a semicolon. So the exact code we'll use for our program is proc gchart semicolon vbar pack category / discrete type equals mean sum var equals tab 12 mdx semicolon. Just like the proc gchart code in univariate graphing, vbar requests a vertical bar chart. The categorical explanatory variable pack category / discrete tells SAS that we want levels of our categorical explanatory variable to be represented on the x-axis. The rest of the code in this statement provides instructions to SAS for how the response variable should be represented on the y-axis. Specifically, type equals mean requests a calculated average, and sum var is short for summary variable. So we're asking for the response variable, tab 12 mdx, to be displayed as a mean on the y-axis. Here's our categorical by categorical bar chart. Pack category, our explanatory variable, is on the x-axis, and this is by the rate or proportion of nicotine dependence along the y-axis. So you can see from this graph, among those smoking 1 to 5 packs a month, about 25% of those individuals are nicotine dependent. Among those smoking 6 to 10 packs a month, 50% are nicotine dependent. Among those smoking 11 to 20 packs a month, 58% are nicotine dependent. Among those smoking 21 to 30 packs per month, almost 70% are nicotine dependent. And among those smoking more than 30 packs a month, more than 70% are nicotine dependent, around 77%. We can also see that these rates form a pattern. That is, the more packs smoked per month, the higher the rate of nicotine dependence. So, in a graphical way, we're already seeing that there seems to be a relationship between smoking and nicotine dependence as we hypothesized. Looking at our graphing decisions chart, we can see the steps we've taken to generate a bivariate graph with a categorical response variable that has 2 categories and a quantitative explanatory variable. We also discussed how to convert the quantitative explanatory variable to a categorical variable, a step which must be taken for the purposes of visualizing the relationship. If our explanatory variable was originally categorical rather than quantitative, we could have skipped this step and just moved on to a categorical by categorical bar chart. What decisions need to be made if the response variable has more than 2 categories? In this case, we would need to collapse a response variable categories into 2 categories. To demonstrate this, we'll have to modify the research question. So let's modify the research question to look at the association between ethnicity and smoking stage. And we'll create a response variable that categorizes young adult smokers into 3 groups: non-daily smokers, daily smokers, and those with nicotine dependence. These are the ethnic groups recorded in the NESARC codebook, along with the syntax that we can use to create a 3-category smoking stage variable. This sample can be described with these 3 smoking categories. This univariate bar chart shows that about 50% of the young adults sampled are nicotine dependent, about 30% are daily smokers without nicotine dependence, and almost 17% are non-daily smokers. However, to examine a relationship between this variable as the response variable in another, we need to collapse this to only two categories. To do this, we need to make some decisions. Here are two perfectly reasonable decisions that we could make. We could examine the association between ethnicity and daily versus non-daily smokers, or we could examine the association between ethnicity and nicotine-dependent versus non-nicotine-dependent individuals, thereby collapsing across these categories in some way. In either case, some data management needs to be added to the program. To collapse the response variable into daily versus non-daily smokers, we use this syntax. If S3A-Q3B1 equals 1, that is, if the individual smokes 30 days a month, then daily equals 1, semicolon. Else, if S3A-Q3B1 is not equal to dot, that is, it's not equal to missing, then daily equals 0, again followed by a semicolon. To graph the relationship between a categorical explanatory variable and a categorical response variable, we use proc gchart, semicolon, vbar, eth raised 2a, which is our categorical explanatory variable, / discrete, type equals mean, sumvar equals daily, our categorical response variable, followed by a semicolon. Remember, our categorical response variable should not have more than two categories or levels, and those two categories should be coded as 0 and 1. 0 represents no or negative observations, and 1 represents yes or positive observations. In this format, requesting the mean of a categorical response variable actually gives us the proportion of 1s or positive observations.
Because our response variable was categorical with more than two categories, we needed to collapse it into only two categories. And because our explanatory variable, ethnicity, was categorical, we created a categorical by categorical bar chart. Had our explanatory variable been quantitative, we would have needed to bin or collapse that variable into categories before creating the categorical by categorical bar chart.
From the two bivariate graphing examples that we've covered, we filled in the left side of our graphing decisions flowchart. Each example showed situations when our response variable was categorical. Let's talk now about the right side of our flowchart when the response variable is quantitative. We'll now change our research question using an example from the Gapminder dataset. Here, we're interested in the association between the percent of the population living in urban settings within each country and the country's rates of internet use. That is, the percent of people with access to the World Wide Web. Below, you can see a full description of these variables from the Gapminder codebook. For this research question, both the response and explanatory variables are quantitative. A bar chart would not work here. The graph of choice would be a scatterplot. A scatterplot, by definition, is a graph of plotted points that show the relationship between two quantitative variables. In a scatterplot, data for each observation's explanatory and response variable are plotted. This scatterplot shows a sample of 11 observations according to the relationship between height and weight. In the lower left-hand side of the graph, we see plotted individuals with relatively low height and weight. In the upper right-hand portion, we see individuals with relatively high height and weight. Returning to the Gapminder dataset, let's see how we can use SAS to examine the relationship between percent of the population living in urban settings and the rate of internet use. Since we're using a different dataset, we'll begin with a new program. It begins with the standard libname statement. Then we're going to call in the Gapminder dataset at the beginning of the data step. We end the data step by sorting according to the unique identifier. In this case, the unique identifier is country. Next is a univariate and variable statement, in order to examine the central tendency and spread or variability of both urban rate and internet use rate. Then the program ends with a run statement. We can see that for urban rate, the mean percent of the population living in urban settings is about 57%. The standard deviation is about 24%, suggesting that there's quite a bit of variability from country to country in terms of the proportion of the population living in urban settings. For internet use rate, on average, about 35.6% of the population across these individual countries has access to the World Wide Web. Again, with a standard deviation of 27.8, there seems to be quite a bit of variability from country to country. But is there a relationship between these two variables? We can explore this question visually with a scatterplot. SAS provides scatterplots in response to the proc gplot command. The code is proc gplot plot quantitative response variable, which is internet use rate, times quantitative explanatory variable, which is urban rate, ended with a semicolon. To characterize the relationship that we see in a scatterplot, it can be helpful to draw a line of best fit through the observations as a way of trying to determine how the dots line up. That is, do they seem to line up in a positive or negative direction, or with a positive or negative slope? An increasing slope, as we have here, between urban rate and internet use rate, indicates the relationship is positive. That is, an increase in one of the variables seems to be associated with an increase in the other. Here's another example from Gapminder exploring the relationship between income per person in each country and internet use rate. Again, if considering a linear pattern, the relationship seems to be positive. That is, higher income is associated with higher internet use rate. The strength of the relationship in a scatterplot is determined by how closely the data points follow the form. In this scatterplot, the data points follow the linear pattern quite closely. This is an example of a very strong relationship. In this other scatterplot, the points also follow the linear pattern, but much less closely. Therefore, we can say that this is a weaker relationship. The form of the relationship is its general shape. When identifying the form, we try to find the simplest way to describe the shape of the scatterplot. There are many possible forms. As we saw, a positive or increasing relationship means that an increase in one of the variables is associated with an increase in the other. And negative or decreasing relationship means that an increase in one of the variables is associated with a decrease in the other, as shown in this central scatterplot. Not all relationships can be classified as either positive or negative. Further, if you can't plausibly put a line through the dots, if the dots are just an amorphous cloud of specks on the graph, then there may be no relationship.
For various reasons, a scatterplot is sometimes limited in its ability to allow us to evaluate a relationship visually.
Here's a scatterplot for income per person by rate of HIV among 15 to 49-year-olds. Since most countries have a low HIV rate per 100 people, the dots on this scatterplot seem to clump in the lower left-hand corner of the graph. So to try to get a better sense of whether or not there's a relationship between these two variables, we would try to categorize or group the explanatory variable income. If we use the proc univariate statement for the variable income per person, we can use the quantiles table to determine the 25th, 50th, and 75th percentile or quartile. These will allow us to divide the countries into 4 ordered groups according to income per person. We need to add the appropriate data management syntax to the program within the data step in order to create these categories. This new variable will be called income group. Proc freq and table statements can be added so we can examine the distribution of this new variable. After the program has been saved and run, we can see the distribution for income group. The 4 ordered groups we created show that there are 47 countries in the lowest income group, the lowest 25%. There are 48 countries in the next 25%, 49 in the next, and 47 countries in the highest 25% in terms of income.
With this new categorical explanatory variable, we're now ready to create the last type of bivariate graph. That is, the categorical to quantitative bar chart.
The code we will use is proc gchart semicolon vbar categorical explanatory variable, which is income group, / discrete type equals mean, sumvar equals quantitative response variable, which is HIV rate, and it ends with a semicolon. In this bar chart, while we can see clear differences in HIV rate based on income per person within countries, the relationship does not seem to be linear. Although we might have expected a negative linear relationship, that is, increases in HIV rate with decreases in income group, you can see in this graph that income group 2 falls outside of this pattern. We've worked through each type of bivariate or 2-variable graph, highlighting when and how each should be used to visualize a relationship. Now, let's just very briefly summarize. When visualizing a categorical to categorical relationship, we use a bar chart with explanatory categories on the x-axis and the proportion of our response variable on the y-axis. When visualizing a categorical to quantitative relationship, we use a bar chart with explanatory categories on the x-axis and the mean of our response variable on the y-axis. When visualizing a quantitative to quantitative relationship, we use a scatterplot, in which each observation is displayed according to the values of the explanatory and response variables.
Use these basic guidelines, as well as the graphing decisions flowchart, to visualize the relationships between your own variables of interest.